Okay, so okay. So this is what actually the waveform will propagate like this, that because of this uh, phase change with distance, okay, that is what we have seen here, that there will be some beta x, okay. So beta x, you know, in waveform equation, we have this, it is a function of t and also a function of x. So function of x means that the wave is propagating along the x direction, and function of t means that there will be oscillation with time. Okay, so that is the general wave equation you have already seen earlier. So uh, this beta basically gives you the phase change with x. Okay, so it is called the phase constant, which is having a unit radian per meter. So with every distance, how much radian phase change is there, that is given by this beta. So you can see that in this waveform, that along the distance x, the phase change is there, and accordingly it gives you the waveform. So basically the waveform, it propagates along x direction because of that beta. Okay. So that beta is responsible for phase change, which means that it will look like a PA. Well, whereas actually the oscillation is along this direction, along the perpendicular direction, the oscillation is there. Okay, but all the oscillations at different points in x are at different phase, and that's why you have this waveform nature. That is how the wave is propagating. Okay, and alpha is the attenuation constant, we have said. So that you can see here, that gradually the amplitude is actually dying out. So that is due to the alpha. So these are the two factors that come into picture when there is the transmission in this transmission line, when the signal is transmitted. Okay, this is what again we have studied in the last class. And then this was the last slide for the transmission line, that if we take the ratio of the forwarding traveling wave and the back and the forward traveling voltage wave and the forward current wave, then the ratio is given by this, which we call it as the characteristic impedance of the transmission line. Okay, Z0. That is called the characteristic impedance. It is somewhat like the Ohm's law, you know. V by I gives you the resistance R. So similarly here, V by I gives you your characteristic impedance Z0. Okay, but this is with respect to per meter. Okay, characteristic impedance. Okay, here all these L, C, R, G are per meter. So accordingly, you have some characteristic impedance. Now this characteristic impedance will, sorry, Z naught is not, the unit is not in terms of meter, because here L and C are per meter, R and G are per meter. So this characteristic impedance will be there for a transmission line which is having R, L, G, C uniform over the whole transmission line. That is required. Okay, that is what I want to mean, that over the whole transmission line, R, L, G, C, if they are uniform, then your Z naught, this Z naught you will be getting it, the unit will be ohm. Okay, this Z naught, the unit is ohm, and that Z naught will be now constant for that transmission line. You can always find out the characteristic impedance of a given transmission line. Okay. Similarly, if I take the ratio of the backward traveling waves, then also I can find out the characteristic impedance, but that will be now minus of Z naught. Okay. This again, you can just later on when you will be studying this transmission line, that time you will see how the things are derived. Okay. Then the next point is that for high frequency, inductance and capacitance effect obviously plays a significant role, and accordingly the phase constant, we'll see that phase constant will increase with as the frequency increases. So as the frequency increases, since the phase constant is increasing, that means over a small distance you have a large phase change. Okay, over a small distance in the transmission line you will be having a large uh, phase change. So that means you will be having an appreciable delay when that transmission takes place over the transmission line. The delay will be very large, because you will be having, so basically you can see here that if this phase change is very high, then this waveform will be like this. Okay, if the phase is changing very fast, then it will be like this. That means something, if you have excited here, it will and the time it takes to reach the other end is many time periods. Okay, many time periods. Okay, the number of time periods it takes to reach the receiver, it will increase. You can understand from the picture here. So if it is more and more flat, that means the delay in the because phase is related to the time delay. Okay, phase is related to the change in phase. The difference in the phase is difference in the time. So that is the time delay. So obviously I will not like to have large phase delay, a phase change from one point to another. Okay, whereas with large uh, omega, if your omega is high, then you will be having large transmission delay, and that will give you your yeah, some appreciable. You can find make out that there is a difference in the time of the speaker and the listener. Okay. And then we'll also see this in a lossless line, R is equal to, where R is equal to 0, G is equal to 0, then you will be not having any attenuation. That can be also checked. Okay. Anyway, before going to the next one, that I said that next one is waveguide. But before going to that, I just want to talk about some of the questions that you raised in the last class. So that time, since I was not having the slides or anything in my hand, I was not able to uh, explain the things. I just told something. So today I will better, I think I'll first explain those things in more details, because some of the things I think that later on it will also be required for you. Okay, so you should have a better understanding. So I have prepared some write up for the questions that you raised in the last class. Okay, so I will first talk about those things and then we'll come back to it. Okay, so just a minute. So this is the, is it visible?
Yes, sir.
Yes, sir.
Yes, sir.
So this is the thing that someone asked me about impedance and admittance. What is admittance and all these things. So these things more or less you have studied in your class 12. Okay, but again I think it is better that to revise it again, because this thing you have to use it again and again. Is throughout your career, in fact. You have to use this concept of impedance, admittance, whenever you are, because you will be working with electrical and electronic circuits. So you have to know these things in better details. So that's why I have prepared this thing. You can read it. So you can see basically first for impedance, I have taken a simple circuit, a series RLC circuit. Okay. Although in our transmission line, we said that there is no C in series. There is only R and L. Anyway, I have taken a general case where R, L, C all are there. Okay. So if Vt is my input voltage, okay, some AC voltage, Vt. So the current that will flow through it is IT. Okay. Now this IT I am taking it to be Im cos omega t plus phi naught. Okay, phi naught is the phase. Now see, this phase is something very relative. Okay, it depends on at what time you say t is equal to 0. Okay, depending on that only you can say what is your phi 0. So, and all the other signals, you can suppose I take one signal as the reference signal with phase 0. Okay, then all the other signals I can always find out how much the phase difference is from that reference signal. Okay, that always can be done. Okay, so here in general I can write it as cos omega t plus phi naught, but then for simplicity and for convenience, what we are doing that we are taking this IT as my reference signal with phase 0. So I make phi naught equal to 0. Okay, hence it is Im cos omega t. Okay, so that is my signal, reference signal with phase 0. Now your VRT, that is the drop across this R, will be equal to RIT, okay, Ohm's law. So that will be equal to this, okay, R into your IT. VLT, you know, it is equal to L di dt. Okay, this is the drop across this inductor, which you will get it like this. Okay, it is minus omega L Im sine omega t, which gives you cos omega t plus pi by 2. Okay, whereas the current, the drop across this capacitor is given by 1 by C I tau d tau integrated from 0 to t. Okay, so it is the integration of IT. Okay, that gives you your VCT, and you get it like this. Okay, these are the expressions for VRT, VLT, VCT. So these are the three drops across R, L, C. So obviously your VT is equal to this plus this plus this at any instant of time t. Okay, at any instant of time t, you can always find out your VT by adding VRT, VLT, and VCT. Okay, so it's just like this, that if IT is given, you can find out VT. If VT is given, you have to find out IT. It's like that. Okay, so that may be the problem in your RLC circuit. Now we generally use phasor diagram to represent an AC circuit. That is for convenience. So we'll see how. Now what is phasor representation? Now suppose I have the signal x1t. I write it as A1 cos omega t. So here I have taken this one as the reference with phase 0. So, sorry, although I have drawn here A1 like this, okay. This one should be A1 cos omega t plus phi naught. You can write it like that. Okay. So, A1 is this. Here I have taken it as a phase in the diagram. Okay. So, I'll make a change here afterwards. So, it is A1 cos omega t plus phi naught, you can say. This is the phi naught. And then x2t is A2 cos omega t plus phi naught plus phi. Okay. So that is your A2. Okay. Now you see how I get this x1t and x1t or x2t, whatever a signal. Whenever these things rotate, suppose A1, this you have something like this. If I keep on rotating, you know this. If I keep on rotating like this, then whatever the projection of this will be on this x-axis, that gives you your A1 cos omega t. Okay, that projection, that is given by the projection of this if it keeps on rotating. Okay, so basically what we do, whereas if it is given in sine form, it will be the projection on the y-axis, that you know. Okay, so basically phasor means what we do is that we take this A1 as a representation, this one, this arrow. I take this one as the representation, which does not have anything to do with the time. So whatever is the time, at any instant of time, whatever is the projection, okay, whatever is the projection, that will give me my signal. So that is how actually a signal is represented in phasor form. It is basically, I am giving you a representation of this x1t in a phasor way, where this arrow, the magnitude of this arrow will be equal to the amplitude, and the direction will be, or the angle will be with respect to the phase. Okay, the angle will be given by the phase. Okay, this will be given by the phase. So that is how any signal can be represented, independent of time. Okay, so at any, so now when I have two signals, how I compare these two signals, because time is not what is making them different. It is what is making them different is their amplitude and the phase difference between them, that is making them different. So when I plot them or I draw them, I draw one arrow corresponding to A1 with phase angle phi, and the other one I draw A2 with the phase angle, whatever is the phase angle, okay, with respect to that. Okay, so accordingly, now when I take x1t is equal to A1 cos omega t with 0 phase, I will be drawing x1 like this. Okay, I'll be drawing x1 in this direction, and this signal x2, since it is having a length of a2, amplitude of a2, I will draw this as a2 and with a phase difference of phi. This is how phasor is represented. Okay, so that is how all the different signals can be represented. They are represented by their amplitude and they are represented by their phase. Okay, that is how they are represented. So these are the two things which are actually defining the signal. So I represent them in this way. However, conventionally we don't take the amplitude actually. Okay, we don't take actually the magnitude equal to the amplitude, but we take the RMS. Okay, the magnitude of the phasor is by convention taken as 1 by root 2 times of the amplitude. What is that 1 by root 2 times? The 1 by root 2 times is the RMS value of x1. What is RMS? Root mean square. And how we calculate the root mean square? This is, you do the squaring, okay? Then you take the mean of it means average, okay? So I take the square of it, integrate it over a time period, divided by the time period, it gives you the mean squared value, and then I take square root of it. So this gives you the RMS value of x1t, which you will find out to be the amplitude divided by root 2. Okay, you can check it. So instead of taking the amplitude as the magnitude of this phasor, conventionally we take the RMS value, which is 1 by root 2 times of the amplitude. Anyway, that doesn't matter, because once you are doing the scaling of all the phasors by the same 1 by root 2, it doesn't matter. Okay, so that is by convention actually we take. So scaling of all phasors by the same factor 1 by root 2 is fine. Means there is no problem with that when we are doing it. So only thing we have to see that the relative magnitude of the phasors and the relative separation of the angle between the phasors. That actually defines the signal. Okay, this defines the signal. Now, as I said, why we use phasor in our AC when we are doing this AC analysis and all these things, the reason is that it helps you, it makes the calculation very convenient. How? See, for example, here, as I said, that if I have to calculate VT, given your IT, I have given you your, at any instant of time t, I have given you that this is your IT is equal to Im cos omega t. I have said that this is the IT. So what is the corresponding VT? So what you have to do, you have to first write down VT is equal to this. Then you have to do all these trigonometric calculations to find out your VT. Okay. So at any point t, what will be the value of VT? You have to do a lot of calculations. Okay. It may not be always easy. Although it's a very simple circuit, that's why it is easy here. But if it is a more complicated circuit where you have R, L, C, some parallel branch and all these things, you have many complicated electrical circuits. So there it may not be that easy. So it becomes easy if we take the phasor diagram, when we represent V and I in the form of phasor. Let us see how. So what we have said that IT, we have said that IT is equal to Im cos omega t. So I take this I. This is the phasor representing your current I. Okay, it is a phasor. Okay. So this magnitude is equal to I, which is Im by root 2. And since we have taken that, we have considered that the current I is with zero phase, so it will be along the zero angle line. Okay, this is my I. Then I know, I have already seen that what is my VR? VR is simply I into the resistance R. So the drop across the resistance will be given by VR, which is equal to your phasor I into R. Okay. One thing note here that these are actually phasors. These are not vectors. Okay. Although I am writing in a vector notation, but in book actually they are written in bold. Mostly they are written in bold. So here I cannot write in that one. So that's why I put one arrow on top. They are not vectors. They are phasors. Phasor and vector, they are different. Although in some cases they can be, you can say they are analogous, but otherwise they are different. Voltage is not of voltage or potential at a point is not a vector quantity. It is a scalar quantity. So obviously voltage cannot be uh, denoted as a vector. Okay. So these are phasors, not vectors. Okay. That you have to keep it in mind. So VR is equal to IR. Okay. This is the drop across the resistance, and since it is in the same phase, okay, as we have already seen that VR is equal to in the same phase cos omega t, there is no phase change, so it will be in the same phase. Whereas as we have seen, this VL is having pi by 2 phase, okay, leading phase, it will be leading by pi by 2, whereas VCT will lag by pi by 2. Okay, there's a lagging phase. So accordingly, I draw VCT at minus pi by 2 phase, and I draw this one as plus pi by 2 phase. Okay, this is how I now draw this VC in the form of a phasor, and VL also in the form of a phasor. Now now here something, it is somewhat like the same vector addition type. Okay, now I want to find out the VR plus VL plus VC, because V is equal to VR plus VL plus VC. So here it is somewhat like the vector addition I do, and then I find this is my V. Okay, here I have assumed that this VL is greater than VC, and hence VL minus VC, here I will be getting it because they will be subtracting each other. They are in opposite phase, and accordingly I can find out your V like this. Okay. Now what is the magnitude of this V will come? Magnitude of the V will come out. You can use Pythagoras theorem or whatever it is, it will come out with this. Okay, this is the magnitude of the, because this one I know it is equal to IR. Okay, I is the RMS value of your current, R is given, similarly L is given, C is given, and for a given omega of your signal, then you can always calculate your V from here. The V will be the RMS value of your VT. Okay, that is the RMS value of your VT. So you get your V. Similarly, phi can be calculated like this. It is from here you can see that how you can get your phi. Phi will be tan inverse of this. Okay. So accordingly, now once you get your V, you get your phi, you can now write down your Vt will be equal to root 2 V cos omega t plus phi. So you see that once I draw it in the form of phasors and all these things, then calculation of Vt is straightforward, almost straightforward. Okay, it is just you draw it, you find out all these values, okay, and you just put it there instead of doing all this. Where here you have to find out all the mathematical manipulations you have to do. Okay, that you need not to do. Okay, just for no, as I am saying here that phasor addition is somewhat similar to the vector addition. Okay, that you can check here. I have given it. If I have x1t like this, x2t like this, then x1t plus x2t, you will find that it is basically this one, which is basically same like the vector addition. Okay, as you do, you can just check it. Okay, this is given here. You can check this is the mathematical derivations of this, and that gives you this one. Okay, so phasor addition is somewhat like your vector addition, not other things. Okay, only the addition of the phasors will be somewhat like the vector addition that you know. You can do it directly using that. Okay. Okay. So now we have already got this V square will be equal to this. This we have got it here. Okay. V square is equal to this. Okay. So I can write it like this. Now I denote this one. This one. I denote it as square of some mod z. Okay. Mod z. What is this z? I define this z as a complex quantity this. You see, if z is defined as a complex quantity like this, then the magnitude of this z will be this. Magnitude of this z will be this root over. So this is basically the square of the magnitude of z. You can just check. Okay. So basically, since I have already got it, v square is equal to this, I now denote this z equal to this. I take z equal to this, a complex quantity, and then the magnitude square of this Z will give you this. Okay. So this Z, we term it as impedance. This is what we call it as impedance. And this impedance is nothing but a complex quantity. It is a complex quantity which is having two parts. One is the real part, the imaginary part. Real part is having the resistance R. You can see that. The resistance R is the real part. Okay. So in a purely resistive circuit, the Ohm's law, in Ohm's law and all these things, when you have studied, you have used only R, no L, no C. So this impedance was a pure real number having only R. Okay, so there was no imaginary part. But whenever there is some L or C or both, whenever that inductance, capacitance, they come into picture, then in your impedance you will be having one imaginary part. Okay, and that imaginary part is given by the inductor and the capacitor, and we call this as the reactance part. This one we call it as the reactance, as I have written here, R plus jx. X is the reactance, X is called the reactance. So imaginary part is called the reactance. So resistance and reactance. Resistance is the real part, reactance is the imaginary part. These two together makes your impedance. Okay. Again, reactance can be divided into two parts depending on whether there is L, whether there is C, or whether you have both. Okay. XL is the reactance due to L, XC is the reactance due to C. XL will be equal to omega L, XC will be equal to 1 by omega C. Okay. Now, as any complex quantity, you know, I can always sketch it in the form of a phasor, polar diagram, and phasor in a complex plane. Okay, in a complex plane that you do. It's very quite common thing that in your, when you have studied in mathematics, in when you have dealt with these complex numbers and all these things, you have drawn the complex numbers in a complex plane. Okay, so similarly, I can also do it here. Okay, so I am drawing this Z is a complex number, which I am drawing it as R, the real part, and it is having your XL minus XC. Okay, so this is the imaginary part, JXL. Okay, and minus JXC. So this is what I have, the X. So it is straightforward. You can understand that this is how I can represent it in a complex plane, this impedance. Okay. And in polar form, I can write this complex number Z is equal to the magnitude of Z and the argument of Z, that is the phase phi. Okay, this is the phi. Now you can check here, this is again, you can check here that here this phi and the example that I have taken here, the phi here, okay, here this phi, two phi's will come out to be same. Okay, so basically this phi here is due to the impedance. Okay, so there is a direct relation between V, I, and Z. Okay, so this phi is actually due to the impedance, this phi. Okay, that you can check that whatever is the phi here, that phi will give you the phase difference between current and the voltage. Okay, so in a purely resistive circuit where phi is equal to 0, then obviously I and V will be in the same phase. Okay. Similarly, if it is a pure inductive circuit, then phi will be 90 degree. So in that case, your voltage will obviously lead the current by 90 degree. So like that. Okay. So we can check what is your phi and all these things. So your Z, I now split it into three parts. One is your Z R with angle 0, XL with angle pi by 2. This is the XL, and XC with angle minus pi by 2. I have basically this impedance is having three parts, real part, and this is the imaginary plus J part, and this is the imaginary but minus J, minus 90 degree phase difference. Okay. So now if we want to write down my output voltage phase in the phasor form, okay, in phasor form, I can write it as V is equal to IZ, okay, that we have seen earlier. V will be equal to IZ, and this Z I write it in a phasor form like this, okay. So your output V will be written in a polar form in the polar form, I can write your V as V phi naught plus phi. Now we have already taken this phi naught for current I, this phi naught, we have taken it to be equal to 0. So your ultimately your V is coming out to be V. V is the magnitude, that is the RMS value of voltage, and phi is the angle, phase angle. Okay. That anyway, I have, so this is what we are getting here. It was what we have already got it in the first first 2-3 slides. We have already got this. The same thing we are also getting it if we are doing the multiplication of the polar form. Okay, polar form. Also, we can expand it. You can just go through. This is the same thing I have done it here. Okay, VR. You can see this is IR. I is 0 phase. R is 0 phase. So IR is 0 phase. So they will be in the same phase. VR and I will be in the same phase. Whereas VL, I is 0 phase. This is XL with plus pi by 2 phase. So when I multiply them, I get IXL and the argument will be added. So it becomes pi by 2. Okay. So it is leading by 90. Your VL will lead I by 90. Whereas similarly in the same way, VC will be lagging. VC will be lagging the I by 90. Okay. So this is what you can check all these things. So ultimately you get your V will be equal to in this form. I can write it in this form. It's just straightforward. You can, I think now it is clear to you that what is impedance, how the impedance term comes actually. This is how it comes. Okay. You can go through it and you will understand the things. Now just few points. If XL is greater than XC, then that means the inductive effect is more than the capacitive effect. Okay. So in this case, you can understand that obviously your voltage, the input voltage will be leading the output current. Or in other way, I can say the current in an inductive circuit, is lagging. It will lag by lag from the voltage, input voltage. The current in a inductive circuit will lag. Okay. If the circuit is pure inductive, then it will lag by 90 degrees. Pure inductive. Similarly, if the circuit is capacitive, XC is greater than XL, that means the effect of capacitance is more than the effect of inductor. Okay. In that case, the current will be leading. Current will be leading the input voltage. Okay. Just the opposite. Here the current will be leading. And if it is a pure capacitive circuit, then current will lead by 90 degrees. Okay. Current will lead by 90. And if XL is equal to XC, then even if there is L and C, but they cancel each other. And then the circuit becomes an equivalently a pure resistive circuit. And in that case, your phase, there will be no phase. Okay, phase will become 0. Even if there is L, even if there is C, it will become, the whole circuit will now function like a pure resistive circuit. And in that condition, you will see that your current, magnitude of the current in the circuit will be maximum. Because I know that I will be equal to V by mod Z. Okay, V by mod Z. But here, since XL and XC are cancelling each other, then since XL and XC are cancelling each other, these are cancelling each other. So your Z is equal to R. Mod Z will be equal to R. Okay. So in that case, your this one I will be equal to V by R, and that is the maximum you will have. V by mod Z, and mod Z is minimum when omega L and omega 1 by omega C, they cancel each other. Okay. And hence you will be having the maximum current flowing through the circuit. The current will be maximum in that case. Okay. And hence that condition is called resonance. That condition is called resonance. So resonance is something like this, that I have one RLC circuit, series RLC circuit, and in the input VT, I keep on changing the frequency, and then I keep on measuring the current, RMS current in the circuit. At some frequency omega, I will see that suddenly the current is very high, and then again if I increase the omega, the current will again keep on decreasing. So that particular omega at which the current is maximum, that is my resonance frequency, at which the XL and XC, they cancel each other. That means at that omega, omega L is equal to 1 by omega C. They cancel each other. Okay, and that frequency is called the resonance frequency, and I can always find out that resonance frequency will be equal to F equal to 1 by 2 pi root LC. Straightforward. Omega L is equal to 1 by omega C. So from there you can just calculate it. This will be your resonance frequency. This is the frequency at which the series circuit will resonate. Okay, for a given L, for a given C. What is the unit of L? L is given in Henry, C is given in Farad. So 1 by root over LC, this actually turns out to be the, sorry, here again there is a mistake. Root LC, this will be in second. So it is per second. The unit of 1 by root LC is per second. Okay. Root over LC, the unit becomes second, so it is per second. So hence frequency will have that unit per second, which is hertz. Okay, so L is given in Henry, C is given in Farad, and accordingly you have this. Okay, and then one more point, power. What is the power that we are getting from this circuit? Power dissipated, the actual available power, PT, is IT into VT. This is the instantaneous. At any instant of time T, the power that you get is given by IT into VT. Okay, that is the power at any instant of time. Now, if I average it over a time period, that what is the average power? Because this, since it is a function of time, it will keep on increasing, decreasing like that. Okay, so let us calculate what will be the average power. If I calculate the average power, the average you have to calculate like this, and then if you do the trigonometric manipulation, you will see that this is equal to VI cos phi. V is the RMS value of your VT, I is the RMS value of your IT, and cos phi. Phi is the phase difference between I and V. This is the phase difference. So accordingly, you will be getting your PU is equal to VI cos phi. Okay. Now, if you see here, what is V cos phi? If you check your phasor, then you will see that this V cos phi is nothing but VR. Okay, this is VR. If you check here, V cos phi is your VR. Okay, so it is equal to VR into I. It is equal to, so your power, average power is VR into I, or you can say it is I square into R. Okay, so I square into R. So that is your average power. So now one thing you can see here, that the actual power, average power that we are getting from a circuit is independent of L and C. That means the power is dissipated only in the resistor, not in L and C. Okay, why? Let us say this VI, so apparent power is actually VI. We know that. Means V is the input voltage, I is the input is the current. So apparently the power that you should get, you know, V into I. However, this is actually not the power which you are actually getting, which it can be used by you, which can be utilized to do some work. Because any electrical circuit is actually designed to get some work out of it. So electrical energy is supposed to be converted to light energy, or it may be converted to mechanical energy, or it may be converted to heat energy, like that. In a heater, it gets converted to heat energy. In a bulb, it gets converted to light energy. In a motor, it gets converted to mechanical energy. So like that. Electrical energy is to be converted to some other form of energy. So that energy will dissipate away from the circuit. That will be going away out of the circuit, electrical circuit, in the form of some other energy. Okay, that is the used or utilized part of the power. But when you are looking into the circuit, I see that the RMS value of the voltage at the source is V. RMS value of the current flowing through the source is I. So that means actually Vi is the apparent power. This is the apparent power, but this is not the power which I am utilizing. What is the power I am able to utilize is Vi cos phi. This is the power which I am able to utilize. Obviously, if it is a pure resistive circuit, their phi is equal to 0, then this apparent power will be equal to your actual power. That is what you have already studied earlier, that in an electrical circuit, the power which is whatever is the power delivered from the source, the same power you get it out from your load. You can utilize it. Whereas here you cannot. So Vi cos phi is the real or the actual power, and we give unit for this as watt. Whereas this Vi we don't write it as watt. Okay, this one we don't write it as watt. We write the unit of this as volt ampere. Okay, so this is the apparent power given in volt ampere or VA. This one we write it in terms of watt. Okay, this is because this is the actual power which we are able to get out of the circuit. Okay, this cos phi is called the power factor. This cos phi term is called the power factor. When I leads V, here we know that phi is negative. Okay, according to our phasor, you know that if V is lagging, that means V is lagging here. So phi is negative. So we assign a negative sign to the power factor. Although you see cos phi here will be not negative. Okay, it will be positive only, but we call it that it is a negative. We just say that it is a negative power factor because here phi is negative. We call it like that. Okay, because here cos phi, although phi is positive or negative, cos phi will be always positive. But still we say that it is a negative power factor. And just the opposite, when I lags, we say that it is a lagging power factor because I is lagging. But the power factor, we say it is a positive power factor. So just keep it in mind here. Leading power factor, but negative sign. Lagging power factor, but positive sign. Okay. And why we have already said, because it depends on your part. Okay. The other part of this apparent power, we call it the reactance power, which is Vi sin phi, and that you can check that it is nothing but I square x. So Vi sin phi is I square x, Vi cos phi is I square r. X is XL minus XC. Okay, so this is your reactance power. Now, where is this going? The unit for this, we write it as volt ampere reactive. You add this word reactive, or we write it as VA smaller. Okay. Now, where is this power going? It is actually, you know, L and C, inductor and capacitor, they are energy storing elements. They are energy storing elements. They store energy, L and C. So, what happens in one half of the cycle, this L and C, they store energy they take energy from the source and store it. Okay. So in one direction, the current flows in one direction. That time the L and C, they will be storing in one half of the cycle. They store the energy. That means, say, when the capacitor is charging, for example, if the capacitor is charging, okay, the voltage is increasing, then the capacitor gets charged and it keeps on storing the voltage. Okay, it's storing the energy. Then in the other half, when the voltage is in the opposite direction, now the capacitor will discharge in the opposite direction because the current will now flow to the source in the opposite direction. Okay, the current will flow back from the capacitor to the source in the opposite direction. So this is the time in the other half of the cycle, the capacitor will now release back that energy to the source. So the energy actually keeps on going from source to the inductor and then inductor to the source back. Similarly, energy will go from source to the capacitor and then again in the other half of the cycle it will return back to the source. So this energy is just keeps on fluctuating from source to inductor, inductor to source, source to capacitor, capacitor to source. So they are ultimately, you are not able to take out that power for your use. You cannot take it. So they are of no use. It is not utilized, that power, that reactance power. Okay. So that is how we say, means this is the way that the power, basically apparent power, is having two parts. One part is utilized, the other part is not utilized. Now, one thing you see, that actual drop in voltage is IZ. This is the total drop I into Z when current I flows through impedance Z. Out of this, IR is called the ohmic drop. I have used this term in the last class also, so I just want to mention what is ohmic drop. Ohmic drop is IR, because Ohm, when he gave his law, that time he didn't talk about impedance, he talked about resistance only. He said his Ohm's law is stated in terms of resistance. So that's why the drop across IR is called the ohmic drop. Okay, although the drop across the impedance also follows the the Ohm's law, because again it is I into impedance. Okay, but still only this part of this IR is called the ohmic drop. Okay, so this is about the RLC circuit series, and here I have given you the idea about impedance. The same thing, if you consider a parallel RLC circuit, you will get the idea of admittance. Okay, you get the idea of admittance from a parallel circuit. So here I am just taking it IT with R, L, C parallel to each other. In our transmission line, we don't have this error. Okay. Again, we have just followed the same thing. You can just look into it. The same thing, only instead of taking V, I have taken here I, and instead of I have taken V. That's all. Okay. And accordingly, again, there it was, the input voltage was divided into three parts: VR, VL, VC. Here input current is divided into IR, IL, IC, because these three currents, they add up to give you your input current I. And accordingly, I have also given all the phasor diagram, phasor things. Now here accordingly, again you will see that your I is equal to G plus 1 by J omega L plus J omega C into V. Here it is just in the opposite way. There it is V is equal to I into something. Here it is I is equal to V into something. And this one now we call it, there we were calling that one as impedance. Here we call this one as admittance. And this admittance, again you can see, here I have a part called conductance. Here I have a part, this is the other part, the imaginary part is called the susceptance. Okay. So admittance is basically equal to the conductance, real part, and the susceptance, which is your imaginary part, in the same way. Okay. So you can just check the same thing. Okay. And we have here, in this case, we have taken more capacitive effect. So that's why the current is leading the voltage. Accordingly, we have taken a phasor diagram and all these things. In the same way, we have done all the analysis, exactly the same thing. Exactly the same thing. Only here we have taken the role of voltage and role of current, they are just swapped. Okay. Otherwise, everything is same. You can see here again that the resonance occurs when your I, this BL and BC, the susceptance due to inductance and susceptance due to capacitance, they cancel each other. Okay, that will be the condition when your this I will be maximum. Sorry, V will be maximum. The output voltage here will be maximum. Okay, when the this two cancels each other, you will be having the maximum output voltage. Okay. In fact, if there is no R, you can see that when they cancel each other, this one becomes like open circuit. So all your input voltage will appear here. Maximum voltage will appear. Okay. And accordingly, in that case also, your resonance frequency will be also given by the same expression. The resonance will be given by the same expression. Output voltage will come out to be maximum, which is I by G or equal to IR. Okay, G is the conductance, which is the reciprocal of resistance.
Sir,
Okay. Ah, bolo.
sir, why voltage will be maximum? Voltage is not constant in parallel circuit. Like it is AC, so we will get same voltage as that of source.
No, no, this is the RMS value. RMS.
Yes, sir.
RMS is squaring, taking mean, and then just taking the root over that. RMS. All this I am taking it to be RMS value. So it is Vm by root 2. Okay.
No, sir. If we take voltage across resistor R, it will be same as voltage of the source. So what will be the
So where there is
maximum?
voltage? Here there is no voltage. It is a current source. You got it? It is a current source, na? IT is constant, not your voltage. IT is constant. Means IT means I, not IT. I shall not say IT. IM is constant. IM is constant, or the RMS value I is constant, not your V.
Sir, what is the current source?
What is the current source?
No, sir. Like without voltage, what is this current source? Like it will be having some voltage.
Which one?
Sir, this source.
Source.
Yes, sir.
No, it's not like that. It's actually okay. Then again in the next class, I will tell you about voltage source and current source. Although actually
He
current
asked
source,
that current source is due to battery something.
it is also due to battery, but I'll tell you in the next class. Okay? Because today
Thank you,
if
sir.
I don't have time, again I'll then add up at one page here and I'll explain that. Actually,
Thank
we
you, sir.
don't have current source. Generally, whatever you see in your day-to-day life, all are voltage sources. Okay, but what is current source? Means a source that keeps on giving you a constant current. That I will tell you. Okay, next class. Okay.
Okay. Thank you, sir.
Okay. So I'll keep your question in mind,
Thank you,
and
sir.
next class I'll explain. See, I want to give you the full
Thank you, sir.
explanation of these things because in future you will be requiring it. So rather than completing your course in a hurry, it's better that whatever I teach you, I try to give you the full concept of it. So next class I will tell you about the current source. Huh? Okay.
Yes, sir.
So
Thank you,
current
sir.
source is what gives you a constant current. Okay. So here Im will be constant in this case. Okay. So next class I will tell you why. Okay. Okay.
Yes, sir.
Okay. So if you have any more question, you can just ask me. Then next class I will answer you. Otherwise, then you can leave the meeting. Huh?
Yes, sir. And sir, please also upload this PDF.
I will upload it. I have found out 2 mistakes in 2 points that I will make a correction and then upload it. Okay.
Okay, sir.
Okay.
Thank you, sir.
Okay. Bye.
Thank you, sir.
Bye.
Thank you,
All.
sir.
Thank you, sir.
Thank you, sir.